Hi, good afternoon, everyone. Today I'm going to present our work, the enhanced dynamic equivalent identification method of large-scale power systems using multiple events. First, I would like to introduce several motivations of our work. Power system dynamic simulation plays a vital role in online transient stability assessment. However, with the evolution of modern power system, dynamic model of interconnected power system has increased in both size and complexity. So therefore, for online stability assessment and predictive control, an alternative to simulating the interconnected power system in detail is needed. So in fact, normally only the dynamics within a small area in a large interconnected power system is of interest, which is often referred as the study area. The rest of the system are referred as the external area. So to reduce the complexity of the full model system, one possible solution is to represent the external system with dynamic equivalents of reduced order using model reduction techniques. So studies on dynamic equivalency have been carried out over the past few decades. One of the most popular methods is the coherency-based method, which separate the generators into different coherent groups and aggregate them. However, the coherency-based method have the following drawbacks. First, these methods are model-based. The fidelity of the detailed model is very important to the accuracy of the derived dynamic equivalence. So in real applications, the modeling of the external system could be inaccurate or even unavailable to a single entity. Also, the coherency also depends on the continuously changing system operating conditions. And during the generator aggregation process, it could also induce some errors due to the omission of the detailed representation of some controllers. So there's another motivation of our work is that we discovered that the linearity of the large-scale system on the boundary between the study area and external area may be underutilized. So to investigate this linearity, we test the superposition principles on the boundaries in our test system. So the superposition principle states that the sum of the response of two individual contingencies should be equal to the response of the scenario where these two contingencies happen simultaneously. So the results of the linearity test in our test system shows that the strong linearity of the timeline flow between the external area and the study area, unless the location is unless the contingency location is very close to the boundary or the size of contingency is too large. So based on this linearity assumption, previously we proposed a measurement-based model reduction approach that does not require information of the external system topology and system operating conditions. So the basic idea of this reduction method is to replace the timelines with dynamic load models. So the power consumed by these load models is estimated using PMU measurements as on the boundaries. Is estimated using the PMU measurements on the boundaries. So this mapping is described by transfer function, assuming linearity on the boundaries. So the equivalent load power is expected to follow the dynamics of the real timeline flow of the full order system. So generally, the main task of this method is the parameterization of the transfer function using only the boundary measurements, with the objective of preserving the dynamic behavior within the study area. So in our previous work, the parameters of the transfer function model are evaluated using simulation data from a single generation trip event called the training event in our work. So the derived dynamic equivalent shows good accuracy when a reduced model is simulated under the same contingency as the training event. However, the robustness of the identified equivalence is questioned when the reduced model is tested under another contingency that is much different from the training event. So in our new work, we propose the idea of multiple training with multiple events, trying to enhance the accuracy of the dynamic equivalent and improve the accuracy of the dynamics within the study area. So here is a general procedure, identification procedure of our work. first we will pick the inputs and outputs of the transfer function. In this case, the input would be the PMU boundary measurements on the boundaries, which could be frequency or voltage measurements, and the output would be a tile line active or reactive power flow. And after we pick the inputs and outputs, we will try different patterns of zeros and poles and adjusted these parameters until the model accuracy is achieved. So for real-time applications prior to the system identification procedure, we may perform mode decomposition method to the PMU measurements to extract the signal within the frequency range of interest. So in our work now, we only use simulation data as our input and output. So as I mentioned before, in our previous work, the training stage only involves single event, making the dynamic equivalent less robust when a test event is much different. So to improve this, multiple event training is proposed in our study. So instead of choosing a training event arbitrarily, we first calculate the similarity of all the recorded events or all the simulated events by calculating the correlation coefficient of the dynamic response of tile line flow between different events. So the correlation coefficient is calculated as follows. So AB represents the dynamic response of the tile line flow in time domain for different case scenarios. So after we get this similarity indexes, I will use the hierarchical clustering algorithm to cluster all the candidate events into different groups. So in this way, we can form a new training set. So this new training set is formed by selecting one or more representative events in each identified group. And then we will merge these events into a large data set, which will be used for system identification. So this identification will estimate still only one set of parameters, but it will yield the best fit for all the selected events instead of only one training event. So now I will present some of the case study results that we have. So the study system that we use is the MPCC 140 bus system. It has the total capacity of 28 gigawatts and 48 machines. So the study area that we pick, and the study area we pick is this area, and the external area is this right area. So we have to reduce this area, and there are two tile lines connecting the external area and the study area from bus 35 to 73, and now is from bus 29 to bus 37. So first of all, we have to test the assumption, the linearity assumption of our work. We will test, and we will use two generation trips at bus 42 and bus 82 to test the superposition principle. So active and reactive power flow of the tile line between the study area and external area are shown in the following two figures. The results show that superposition principle is valid. So we also test several different event locations in the same way, which shows strong linearity on the boundaries unless the contingency location is very close to the boundary or the size of contingency is too large. So after we test this linearity assumption, we first validate the single event training method that we proposed previously. So we use the generation trip at bus 61 as the training event for parameter identification. So we all use second order transfer function structure, and the inputs of our transfer function are the frequency and voltage measurements at the two boundary points, bus 37 and bus 73. And and we simulate first we simulate the reduced model under the same contingency as the training event. So the results shows that the power consumed by the equivalent loads matches very well with the original power flow of the full order model. So next, to test the robustness of this identified equivalent, we applied another generation trip event at bus 98. So the comparison of the tile line active flow is shown in the right figure. So they demonstrate that when a testing event is significantly different from the single training event, the performance of the dynamic equivalent in capturing the dynamics of the study area is compromises. So you can see the power consumed by the equivalent load stars deviate from the full model response at about 2 seconds. So to improve the robustness of the dynamic equivalence, we have to apply the multiple events that we propose in our new work. So first, as discussed before, we have to choose a large data set that contains all the candidate training cases. So in this study, we choose all the single generation trip events within the study area as the candidate events. So there are 38 events in total. So next to categorize these candidate events into different groups, we calculate the correlation index that we mentioned before, which describes the similarity of the between different case scenarios. So also we create a color map that provides the visualization of the calculated correlation index. And the red color means that they're high and their correlation is higher. So it means that the two case scenarios are more similar. So after we calculate the correlation indexes, we use the clustering algorithm to cluster all the candidate events into the following 5 groups. So then we can form a new training set, which is training set 2, that includes multiple events by selecting representative events in each group. So next step, we will validate the multiple events training idea versus the single event training idea. So to test the effectiveness of this multiple events procedure, we tested the following scenarios. The first scenario is the generation trip at the 53, a 300 megawatts trip. So this generation trip belongs to the same group as the single training set 61. So another scenario is generation trip is 98, which is 600 megawatts trip. So this generation trip belongs to different groups as the event used for single event training. So we want to see the performance of the dynamic equivalence in these 2 scenarios. So for scenario 1, the testing event belongs to group 1, which is the same group as training set 1. It can be concluded that both dynamic equivalents identified using different training sets match very well with the full model response during the first 2 sprints. However, after 4 seconds, it is obvious the performance of training set 2 shows improvement over training set 1. So this demonstrates that even when the testing event is similar to the training event, multiple events training could still enhance the accuracy of the dynamic equivalence. For scenario 2, the test event belongs to group 3, which is significantly different from training set 1. So it shows that the dynamics of the reduced model derived using training set 1 poorly matches with the full model response. By contrast, the accuracy of the equivalence identified using multiple events enhance the matchness very greatly. But it is noted that there is still a small discrepancy between the response of training set 2 and the full model response. This could be explained by the trade-offs between accuracy and the number of multiple events involved in the training, given the structure of the transfer function model. So it means that maybe when we choose more complex structure, we have the ability to include more multiple events, and in this way we can better enhance the accuracy of the equivalence. So to sum up, our work proposed a measurement-based reduction approach to derive a reduced dynamic model that preserves the dynamics within the study area. So this is all based on the underutilized linearity assumption of the interconnected power system on the boundaries between external area and study area. So we used grid events to identify the parameters of the transfer function coefficients, and to improve the robustness of the dynamic equivalence, we proposed multiple events training in the identification process. So for the future work part, we consider the application in a much larger scale system, for example, the interconnection power system. And we also like to try more complex model structure, like more high order of transfer function, or include more inputs in the transfer function structure. And we also like to try different types of training events, for example, like line trip and bus forward, even composite forts for the identification for dynamic equivalence. And we also consider practical concerns for online applications. For example, the update interval of this dynamic equivalence when system conditions change significantly on online applications, or something like the data processing of the measurements, PME measurements in online applications. Yeah, so that's pretty much all the presentation, and welcome for any questions.
Okay, thank you very much. I think that you have a couple of questions. You can have a look on them. The first question is, what do you believe is the reason for the steady state bias between the simple model and the full model on pages 7 and 8?
Okay, let me see. Yeah, so yeah, we did
could you please
let me show. Yeah, I will show you. Yeah, I will show you the slide.
The audience. Okay.
Can you see the slide?
Yeah, very good.
Yeah, I think they mentioned this one. So I think there's a discrepancy between the steady state value of the active power because the structure that we use is still second order structure. It has some errors. We also only use 2 inputs. So if we try a more complex model structure, it should improve this matchness between the full model response and the reduced model response. So I think that's because the current model structure kind of may still have some inaccuracies.
So would you say that your equivalent is good to capture the dynamic behavior, but is not so good just to capture the new steady state operating point after the disturbance?
Yeah, I think for the current model structure, it is. I think it's the main idea of this work is to capture the dynamics within the study area, especially the dynamics within the first 2 swings, which is very important for transient stability assessment.
Okay. There is another question, but I'm afraid we don't have much time. There are 2 more questions. I would appreciate if you could answer through the the Q&A window. Okay, thank you very much for your excellent presentation and very interesting.
Thank you.